Welcome back to the Real Number System. Today, we'll be talking about section 3.2, where we'll be studying the addition of whole numbers. Now, there's a lot of information packed into section 3.2, so I've divided this section into 3 different videos for you. In the first video, we'll talk about models for addition and properties for addition. In the second, we'll talk about many different algorithms that we use for addition. And then in the last video, we'll talk about adding numbers in different bases, and then we'll talk about mental computation and we'll talk about estimation. Let's get started. As a reminder, the set of natural numbers is the numbers 1, 2, 3. These are our counting numbers. If we add 0 to this set, we have the set of whole numbers. Addition is what we call a binary operation because we have 2 numbers that are combined to form another number. When we add 2 numbers together, we'll call these 2 numbers, say, A and B. These are called our add-ins. And the answer that we get when we add is called our sum. So in our example, A and B are our add-ins, and C is our sum. The first model that we have for addition is called the set model. We talked about sets in the last chapter. In the set model, we're putting 2 sets together. Now, one thing we need to watch out for is our sets have to be what we call disjoint. We can't have any overlap between our 2 sets. In example 1, Jane has 5 blocks in one pile, 3 blocks in another, and she combines the 2 groups. So how many objects are there in the combined group? We draw 5 blocks to represent the first pile. We draw 3 blocks to represent the second pile. These are disjoint sets, 2 totally different groups, totally different piles. And when we put these 2 together, we have a total of 8 blocks. In our next example, Juan has 3 cars in one pile and 2 cars in another. If he combines the 2 groups, the 2 piles, how many objects are there in the combined group? I'll use dots to represent our cars here. So Juan has 3 cars in our first pile. In the second pile, he has 2 cars. We push the groups together to make one big pile, and we have 5 cars in this pile. Again, notice that our groups, our piles, are disjoint. They don't overlap. They don't have anything in common, so we can add 3 plus 2 to get 5. As I mentioned, our sets must be disjoint, have nothing in common. If our sets have something in common or they overlap in any way, when we add the 2 sets together, some elements of the sets are double counted, and this leads us to an incorrect conclusion. If A and B are disjoint sets and we form the union of those sets, then we add the number in each set together. In our next example, Miss King, her first grade class, has 12 boys and 13 girls. All the children in her class own either a cat or a dog or both. Part A asks us how many children are in Mrs. King's class. Well, these are 2 disjoint sets, so we can add the number of boys plus the number of girls. 12 plus 13 gives us a total of 25. In Part B, we have 15 children who own a cat and 6 who own both a cat and a dog. And we want to know how many children own a dog. Now notice these sets overlap. We have some children who own a cat, some who own a dog, and some who own both. So this leads us to a new formula. The number of children who own a cat or a dog, remember our union symbol means or, is the number who own a cat plus the number who own a dog. Now because some children own both, they're counted in both of these sets. To account for the double counting, we subtract the children who own both a cat and a dog. Remember, the intersect symbol from our sets means and. In Part A, we learned that there were 25 children in Mrs. King's class. Part B tells us there are 15 children who own a cat. Let's use X to represent the number of children who own a dog because we don't know how many children own a dog. We do know how many own both a cat and a dog, so we subtract 6. 15 minus 6 is 9. To solve for X, we subtract 9 from both sides, and that leaves us with 16. Our next example is about an ice cream store. There were 300 customers who came into the ice cream store, and they all bought chocolate ice cream, vanilla ice cream, or both. Notice again, we have the overlap here, so we can't just add the chocolate plus the vanilla. We have our new formula. The number who ordered chocolate or vanilla is the number who ordered chocolate plus the number who ordered vanilla minus the number who ordered chocolate and vanilla. There were 300 customers who came into the ice cream store. 200 ordered chocolate, 150 ordered vanilla, and we want to know how many ordered both, so minus X. 200 plus 150 is 350. Subtract 350 from both sides, and on the left side we have negative 50. On the right side, we're left with negative X. Divide both sides by negative 1, and we get that there were 50 customers who ordered both chocolate and vanilla ice cream. Our second model for addition is the number line, or sometimes called the measurement model. Any line that's marked with 2 fundamental points can be used as a number line. The 2 fundamental points are 0 and 1. Kenzo has 5 feet of red ribbon and 2 feet of white ribbon. How many feet of ribbon does he have altogether? I typically count from 0 to 10 on my number line. If you need some more than 10, you can always extend your number line. The first measure we have is 5 feet. So I'm going to make a jump from 0 to 5. I show that jump with an arrow. Then the next measure is 2 feet. So I'm going to jump 2 more places. I have an arrow of length 2. And that lands at 7. So that tells me Kenzo has 7 feet of ribbon. One day, Laura drank 2 ounces of orange juice in the morning and 3 at lunchtime, and no more orange juice throughout the day. So how many ounces of orange juice did she drink for that day? Again, we're going to use the number line model. Draw your number line and number from 0 to 10. Our first measure is 2 ounces. So I start at 0 and I take a jump of 2 and represent that with an arrow. My next measure is 3 ounces. I represent 3 ounces with another arrow starting at 2, and I count over 3 places on the number line. I land at 5, so that tells me that Laura drank 5 ounces of orange juice. When we think about ordering whole numbers, we think about our less than sign. So A is less than B if and only if there's a number that we can add to A to make B. So we're asked to use our definition to explain why 1 is less than 4. Well, the question I ask is there a number I can add to 1 to make 4? Yes, I can add 3 to 1 to make 4. Because I have a number I can add to 1 and my sum is 4, 1 is less than 4. On the screen, we're going to talk about a couple more symbols. So first, we have the less than or equal to. This means that A could be less than B, or it might be equal to B. We also have the greater than symbol. A is greater than B is the same as B is less than A. You may have heard in elementary school that the alligator always opens his mouth to eat the bigger number. So notice when I switch the order of the A and B, the alligator is still opening his mouth to eat the A. In our example, 5 is greater than 3 is the same thing as saying 3 is less than 5. 5 is the bigger number, and the alligator is hungry, so he's eating that bigger number in both notations. We want to fill in these blanks with the less than or a greater than. In part A, 5 is less than 8. Notice again that the alligator is opening the mouth to eat the bigger number, which is 8. 9 is greater than 3. 0 is less than 5. And 7 is greater than 1. It is important for students to master basic addition facts. So we have several strategies to help them do so. One strategy is called the counting on strategy. For example, 5 plus 3 can be computed by starting at 5 and counting on 3 more numbers, 6, 7, and 8. So let's find 7 plus 4 using our counting on strategy. We start with 7, then I'm going to count on 4 more numbers, 8, 9, 10, and 11. So 7 plus 4 is 11. Another strategy is our doubles strategy. If children know something like 3 plus 3, they can easily figure out what 1 more or 2 more than that double is. For instance, 6 plus 7. Well, if a child knows that 7 is 1 more than 6, and so we have a 6 and a 6, which is 12, and 1 more than that would be 13. We're using the associative property. Associative property changes the grouping. So let's look at an example. We're going to find 7 plus 9 using our doubles strategy. So I'm going to bring down the 7. Because I want to think about doubles, I'm going to rewrite 9 as 7 plus 2. Or a child may not necessarily rewrite it, but they'll be thinking that in their head. Well, 7 plus 7, that's our double. 7 plus 7 is 14, plus 2 more is 16. Another strategy is the making 10 strategy. So we want to make 10 because 10 is easy for most children to add. Let's start with 9 plus 8. So 9 plus 1 more would be 10. So I'm going to rewrite 8 as 1 plus 7. Regroup. So 9 plus 1 are grouped together. That's 10. And 10 plus 7 is 17. Let's find 8 plus 4 using our making 10 strategy. So bring down your 8. 8 plus 2 more is 10. So I'm going to rewrite 4 as 2 plus 2. 8 plus 2 is our 10, and 10 plus 2 is 12. As we've been talking about these strategies, you may see some show work questions on your quiz. The work that I have shown with each of these strategies is what I would expect to see on your quiz. Now, by the way, this work would probably be done mentally by the children, but on your quiz, you'll have to show that work. Our next topic is our whole number, our properties for whole number addition. So we have first what's called the closure property. The closure property tells us if we add 2 whole numbers, then we get a unique whole number. So what the closure property implies is that the sum of 2 whole numbers exist, and that sum is unique. In other words, 5 plus 2 has a unique answer of 7. We want to know if each of the following are closed under addition. As I look at set A, I notice that all of these are even numbers. This one is closed under addition. Because when we add 2 even numbers together, the sum is still an even number, so it's in that set. Part B is not closed under addition. In this case, When I add 1 plus 10, I get 11, and 11 is not part of our set. Our next property is the commutative property. The commutative property tells us that the order doesn't matter when we add. 3 plus 4 is the same thing as 4 plus 3. They both have an answer of 7. The next property is the associative property. We've already talked a little bit about the associative property. The associative property changes the grouping, or think about who's associated with each other. For instance, in this example, on the left side, 5 plus 2 are grouped together, and on the right side, 2 plus 4 are grouped together. We always start with parentheses, so on the left side, 5 plus 2 is 7, and on the right side, 2 plus 4 is 6. 7 plus 4 is 11, and 5 plus 6 is 11. So when I change grouping 5 and 2 on the left side to grouping 2 and 4 on the right side, I still got the same answer. Our last property for the addition of whole numbers is the identity property. If we add 0 to anything, like 1, we get that number. Or, for example, 4 plus 0 is 4, or if I say 0 plus 4, I still get 4. So because we get the same thing, it's called the identity, and because we're adding, it's called the additive identity. Which properties of whole numbers are illustrated in each of the following statements? In part A, notice that the order changes. This is our commutative property of addition. In part B, we're adding two whole numbers together and we're getting a unique whole number. This is the closure property of the addition of whole numbers. Now part C is a bit tricky. You see the parentheses and most people want to think automatically this is the associative property, but that is incorrect. Notice we didn't change the numbers that are grouped together. 3 and 5 are grouped together on the left side, and 3 and 5 are still grouped together on the right side. However, what changed is the order in those parentheses. So this would be the commutative property of addition. In part D, we do change the grouping. On the left side, we have 8 plus 5 grouped together. On the right side, 5 plus 2 are grouped together. When we change the grouping in addition, that is our associative property. Join me for our next video when we'll talk about the algorithms for addition.